In our previous lecture, we examined binary outcome models from a purely statistical perspective, namely as a model for the probability that y equals 1 given x, when y is a binary random variable. It turns out that there's another way of thinking about these models, and one that relates them to economic models of rational choice. This is the so-called random utility or discrete choice approach. Random utility models provide not only a novel interpretation of probit and logit, but a framework for constructing richer models of choice for discrete outcomes. We'll begin with some basic terminology. In a discrete choice model, a decision maker, a household, person, or firm, chooses from a collection of alternatives, products, or actions to maximize her utility. We call the set of all alternatives that are available to the decision maker the choice set. We will assume that our choice sets satisfy the following three conditions. First, choices are mutually exclusive. Second, the choice set is exhaustive. And third, the number of alternatives is finite. The first of these conditions says that Alice, our decision maker, chooses only one of the alternatives. The second condition says that the choice set contains every alternative, or to put it another way, that Alice always chooses something from the choice set. In fact, these first two conditions are not restrictive. If necessary, we can always redefine the choice set so that it satisfies them automatically. Suppose, for example, that Alice is at a restaurant and this restaurant serves beer and pizza. Unless this is a very strange restaurant, the choice between beer and pizza is not a mutually exclusive one. There's nothing to stop Alice from ordering both. In this case, the appropriate choice set is not beer, pizza, but rather beer only, or pizza only, or beer and pizza. Unless beer and pizza are the only things on the menu, however, this choice set is not exhaustive, but that too is easy to correct. Simply add a default option. For example, beer only, pizza only, beer and pizza, or something else. Now we have a choice set that satisfies all the restrictions on the slide. Before we can go further, we need to define some notation. This discussion will follow, for the most part, Train's 2009 book. So I just want you to be aware that some of the notation I'm using in this lecture is a bit different from what I've used in earlier lectures. So just make sure you stay alert to that fact. There are capital N decision makers indexed by lowercase n. So lowercase n runs from 1, 2, 3, all the way up to capital N. Each decision maker chooses between capital J alternatives, where alternatives are indexed by little j, so little j runs from 1, 2, 3, up to capital J. We will define capital U subscript nj as the utility that decision maker n obtains if she chooses alternative j. And we will assume that choices are rational. So Alice chooses the alternative that maximizes her utility. Yes, expressing this using the notation I've just defined, we say that decision maker n chooses alternative I if and only if UNI is greater than UNJ for any j not equal to I. Utility, of course, is unobserved. So if we want to model choice, we need to specify what it is that we do observe. The basic idea behind random utility models is to back out preferences from observed choices and attributes given the assumption of rational choice. We will assume that the researcher observes the attributes x and j of each alternative, so these could be things like product characteristics, possibly the attributes Sn of each decision maker, for example, demographics, and also the choice that each decision maker actually makes, although not, as I mentioned before, the utilities themselves. So attributes of an alternative might be something like the price of beer or the kind of pizza. An attribute of the decision maker could be age or sex or education, etc. we will assume that the researcher is able to specify a function called VNJ that relates these attributes, namely those of each alternative j and of each decision maker n, to that decision maker's utilities, UNJ. We call VNJ the representative utility. And to drive home the distinction between V and U, I will sometimes call U the true utility. In effect, V is the part of U that is explained by the attributes that we can observe. We call the leftover piece, epsilon, the error term. To obtain an econometric model to which we can apply probabilistic reasoning, we need a source of randomness. Rather than treating a given person's choices as random, we will instead view randomness as a feature of our sampling procedure. So something that arises from differences between people that aren't captured in our model of representative utility. Such differences are often called unobserved heterogeneity, and the basic idea is follows. Define the error term epsilon nj as the difference unj minus vnj. This is the difference between a person's true utility and her representative utility. Because there are capital J alternatives, this means that there are capital J error terms for each decision maker, namely the vector epsilon with elements epsilon n1, epsilon n2, and so on up to epsilon nj. This vector of errors represents unobserved factors that affect choices but are not captured by our model, namely the representative utilities. So we'll treat these errors as random in the following sense. Take Alice and Bob. Alice and Bob, along with all their fellow decision makers, n equals 1 all the way up to capital N, are a random sample from some population. In this population, some decision makers with the very same attributes are going to make different choices. People are different. This means that those people who make different choices must have different error terms. We can represent these differences in the population using a probability density function. We will call this f of epsilon n, where again, this epsilon is a vector. From this perspective, then, drawing a decision maker at random from the population is the same thing as making a random draw of epsilon according to this density f. So the point here is that it's not Alice's choice that's random, it's the fact that we sampled her from the population that is. Using this formulation, we can calculate choice probabilities, namely the probability that decision maker n chooses alternative j. We define choice probabilities as capital P subscript ni, and these are the probability that uni is greater than unj for any j not equal to I. And we can calculate this probability by taking an integral over the distribution of the errors as follows, where all that I've done here is I've substituted our expressions for u in terms of v and epsilon, and just rearranged the inequality for u to get the epsilons on one side and the v's on the other side. And just notice the order of the indices. So that's epsilon nj minus epsilon ni on the left-hand side, and it's vni minus vnj on the right-hand side of that less than symbol. That's all been a bit abstract, so let's try to take a look at the big picture. We now have all the ingredients that we need to give an overview of random utility models. The basic idea consists of 4 steps. First, we write down a parametric model for V, the representative utility, in terms of the attributes x and s, and a vector of unknown parameters theta. Next, we choose a distribution f for the error terms, that is to say, the unobserved heterogeneity, which is represented by the vector epsilon n. Third, we calculate the choice probabilities as a function of the parameters using our distribution f from step 2. Finally, in step 4, we use observed choices and attributes to back out the maximum likelihood estimate theta hat of the parameter vector theta, which is a feature of our model for the representative utilities. Looking back, it turns out that logit and probit can be viewed as special cases of random utility models, namely models that arise when we consider a choice between two alternatives. But what's, I think, more interesting and much more important is to realize that random utility models provide a framework that we can use to specify and estimate much more complicated models of choice. To make things more concrete, let's consider a very simple example. Suppose that there are exactly two ways to get to work, by car and by bus. We observe two attributes, the cost in time and the cost in money of each mode of transport, capital T for time, capital M for money. Now suppose that we specify the following model for representative utilities with unknown parameters beta and gamma. Namely, the representative utility of traveling by car is beta times the time cost of traveling by car plus gamma times the money cost of traveling by car, and similarly for the representative utility of traveling by bus. Of course, the true utilities are not equal to V, they are V plus the error term. So associated with each mode of transport, there is an error term epsilon that specifies the heterogeneity that we do not observe, differences in people's preferences that are not represented by V. In this admittedly very simple example, the choice probabilities can be written as follows. P car is the probability that epsilon bus minus epsilon car is less than V car minus V bus, while P bus is equal to the probability that epsilon car minus epsilon bus is less than V bus minus V car. And notice that because there are only two alternatives, P bus must equal 1 minus P car. It's because you have to choose one of these two ways of going to work. Our goal when estimating a model like this would be to learn the parameters beta and gamma. These control the effects of observed heterogeneity, namely the time and money costs, which could depend on what we know about each decision maker. So for example, perhaps Alice lives next to the bus stop. Then her time cost of taking the bus is low. Perhaps Bob is 70, so he gets a discount on public transport. Then his money cost of taking the bus is low. And perhaps Clara and her roommates work at the same office, so they can carpool. In this case, Clara's M car is low. The error terms, again, represent unobserved heterogeneity. So if James hates to drive, then for him, epsilon car minus epsilon bus would be negative. But if Steve loves driving, then for him, epsilon car minus epsilon bus would be positive. As described a few slides back, a random utility model combines a specification for the representative utility V in terms of an unknown parameter vector theta with an assumed density F for the errors. I'll now explain how we can write down the likelihood for such a model, which will allow us to estimate and carry out inference for theta. First, a bit of notation. Let yn, which is a random variable with support set 1 up to capital J, denote decision maker n's choice from among all the alternatives, and let zn denote the vector of all attributes for decision maker n, potentially including both attributes that are fixed across alternatives, Sn, and attributes that are not, Xnj. Using the integral expression from a few slides back for the choice probabilities, we can view Pni as a function of theta, namely the conditional probability that yn equals I given the covariates Zn evaluated at theta. In some cases, we can work out a closed-form expression for this function. An important case is the so-called logit family of models, which give rise to the following choice probabilities as a function of the representative utilities Vnj. Unfortunately, models like this are quite rare. For most densities that we might choose for the error terms epsilon, even including such innocuous ones as a multivariate normal, the integral from a few slides back has no closed form. In such cases, we cannot evaluate the choice probabilities directly and must instead rely on numerical approximations or simulation-based methods. But even when we can't write down a simple formula for the choice probabilities, they are still a function of the parameter vector theta given the observed attributes z. So the hard part about random utility models is calculating choice probabilities. Given the choice probabilities, however, the likelihood is quite straightforward. Conditional on the attributes z, the observed choice, yn, is a random variable with support set 1, 2, up to j, and the probability that yn equals j, conditional on z, is simply equal to p and j. Now we can write this as the product from j equals 1 to capital J of p and j raised to the power, the indicator that yn equals j. So this indicator function equals 1 if yn is equal to j, and 0 otherwise. Notice that this is basically the same notation that we used when we looked at index models in our previous lecture. It's just that here, rather than having a product of two terms, we have a product of j terms. Because of this expression, given a random sample of n observations of the choices y and the attributes z, the log likelihood takes the following simple form. It's a double sum over all the decision makers, n equals 1 to capital N, and all the alternatives, j equals 1 to capital J, of the indicator that decision maker n selected alternative j, multiplied by the log of the choice probability p n j, which, as explained above, is a function of theta through the integral that determines the choice probabilities. Notice that this expression holds for absolutely any random utility model. The differences between different models come from different choice probabilities, and these different choice probabilities in turn come from different specifications for the representative utility Vnj and error density F.